Bam Adebayo broke math. No, Adebayo, we need math. Why? His 83-point game was 8.5 standard deviations above his career average. That's a 1 in 53 quadrillion chance. So one of three things has happened. One, someone's wrong on Twitter. Two, NBA points per game are not normally distributed. Or three, we just witnessed an event that has a 1 in 53 quadrillion chance. Whoa! Okay, it's probably not number three. The NBA has a free API, so we can just download a huge set of statistics about players. We can get player, game, points per game over time. We can ask if the data is normally distributed. A normal distribution, remember, says that most of the time you're going to have an average number of points per game. The units on the bottom are standard deviations. And so it says symmetrically you're going to do one standard deviation better than average as often as you do one standard deviation below average. And we just know that's not true with basketball because it's impossible to score negative points. Meaning if you on average score 10 points a game, you could score 21 points in a game. You could score 11 points above average, but you can't score 11 points below your average because you can't get -1. You could have an awesome game and score 50, you can't score -30 or whatever. Normal distributions have two properties we can talk about. Skewness, which is like how far do your tails go off? That's like this part of the distribution. In the normal distribution, the tails go off equally far on either side. But if we're skewed, the tails are going to go off further on one side than on the other. So if we have a positive skew, it means we've got more of a tail on the right-hand side compared to the left-hand side. A negative skew is just the opposite. And we know since you can't score negative points, you can't score on the left-hand side of your average, that NBA games should have, NBA points per game should have positive skew. Second is kurtosis. Kurtosis is like the shape of this distribution. High kurtosis would be like a spire, like a big peak with more probability mass out in the tails, lots of more outlier events. And low kurtosis is the opposite, not a spire, but it's like a broad, flat hill with a lot of probability mass in the center in this wide, flat hill and less probability out on the outliers. So leptokurtic, high kurtosis, spire. Then the normal distribution in the middle, and platykurtic, low kurtosis, hill. With NBA data, what we can do is get players who have played 100 plus games, throw out games where they didn't score any points, and then we can look at the distribution of their points per game. On the x-axis, we have the skewness. How shifted are they to the right? How extended are their tails to the right? Outliers. And on the y-axis, we have the kurtosis. Remember, that's the spire, more outliers. If they were normally distributed, it would look like this. This is simulated data where for every one of the NBA players, I use a random normal distribution using the player's average points per game and their standard deviation to generate this plot of skewness and kurtosis. And what you see is that the skewness and kurtosis, it's all just randomly scattered around zero. But the actual data looks incredibly different. So this is telling us that the players are not normally distributed. Their points per game are not normally distributed. Instead, it seems like there's a lot more skew. So further right tail, which we know it's impossible to score negative points. And also that there's more kurtosis, meaning sharper spire around the middle, but more probability mass out on the edges. There's more extreme outliers, especially with players who tend to have lower average points per game. So back to this. This is the right answer. Points per game are not normally distributed in the NBA. How are they distributed? Another distribution is the Poisson distribution, which is used for number of events occurring in a fixed interval of time, like number of shots you make in an NBA game. Poisson is not perfect for this because in a Poisson distribution, variance is the same as mean. Variance is the average squared distance from average. So it's like how much do you vary? How much variation is there in the data? And each point in this plot is an NBA player. And on the x-axis, it's their average number of points per game, the mean points per game. The y-axis is the difference between the variance and the mean. So if this were perfectly suited for a Poisson distribution, they'd all be around the dashed red line at 0. They have the same variance and mean. But of course, they have much more. Every NBA player has variance that's greater than the mean. So it's kind of like a Poisson distribution, but not a perfect fit due to the mean variance thing. A Poisson-gamma mixture is like a Poisson distribution, but it has an extra gamma parameter so that it gets the useful property that its variance can be greater than the mean. Basically, it's like saying an NBA player will score an average number of points per game, but we acknowledge that there's a lot of variance on top of that. So it might be you didn't sleep well, or you were drinking a lot last night and now you're just going to play poorly, or you're uniquely good or uniquely bad against the players on the other team, whatever. There's a lot of day-to-day, game-to-game variance, which is exactly what we see in the actual data. So we need to give our Poisson distribution an extra parameter to take care of that. So together, here's our skew versus kurtosis plot. This is simulated with a normal distribution. This is what it should look like if the data was normal. This is what it actually looks like. And this is simulated with the gamma Poisson mixture, which is also called the negative binomial simulation. Anyway, you can see this plot with the simulated gamma Poisson looks a lot closer to this plot, the actual data, than it does to the normal distribution. So for Adebayo specifically, the odds of the game are more like 1 in 10 million, not 1 in 53 quadrillion. And then if you think about how many NBA games have there been and how many NBA players are there, it's not unreasonable to think that we'll see a 1 in 10 million or a 1 in 9 million-ish event. And of course, the distribution I'm showing here, this model isn't perfect. It's not exactly the same behavior as this. So those odds are just kind of like an estimate, but I think a better estimate than 1 in 53 quadrillion. Thanks for your time.